All right, I think we'll get started. So you should have your exam 4 written grade done. There's 1 or 2 that I just need to look for, so make sure to check that out. Also, SRTEs are available, so please fill out the SRTE. Please do the homework 10. You know, over the summer and the fall, I always look at the SRTEs and homework 10 and try and figure out, you know, how to change the class for next year. So you're especially helping the people that are going to come after you in MATSE 202 when you do that work. So don't forget to turn in homework 10. I had some extra PLAs. They'll help you think about the material in the last week, so they're worthwhile to do. So I posted 2 PLAs due on Wednesday and 2 due on Friday. They won't take very long. The homework won't take very long, but there are, you know, 3 or 4 questions from this week on the final, so you want to pay attention to the work. Check your grades. Make sure you're up to snuff. I'm going to post the Canvas either tonight or tomorrow, so we'll be on the same page for Canvas. But if I'm missing something or you're missing something, let's chat about it. You saw in the announcements that I have extra office hours. I listed those in the announcements. I'm also going to post the review PowerPoint right when I get back to my office, so you'll see that. We'll talk about the final. There's a final practice exam on Canvas too. And so we should be good to go for the last 3 lectures and for finals week. Any questions or comments? All right. So don't forget the SRTE. So we're going to talk about conducting polymers today, and we're going to talk about some properties that aren't commonly thought about when you think about plastics. Most often, when you think about polymeric materials, you think about what? Insulators, plastics, the coating that goes over the wire, right? You really don't think about conducting polymers that are used for the things that we'll talk about today. One really cool thing where polymers help usher in this digital age and have for the last 30 or 40 years is that you need polymers to do photolithography. So photolithography is how they make Pentium chips and how they make all computer chips. And the chemistry that was invented to do this photolithography was invented at Kodak in Rochester, New York, and at Cornell. And the people who invented it are still alive. And so the folks, once they figured out that they needed high density transistors, the people who invented this polymer chemistry to make positive and negative tone photoresist, you can go hear them talk at meetings. A couple of them have given lectures here at Penn State over the last couple of years. And so this is a real enabling technology for our digital age. And of course, Pentium chips look like this. So these are all Pentium chips, and these are tens and hundreds of layers of UV photolithography, depositing down the traces or the P and N dope layers of silicon, and then stripping away the polymer and putting another layer. And this is really interesting because it turns out that what's the wavelength of UV light? So if we're going to do UV photolithography, does anyone know the wavelength of the UV light? Approximately. Little shorter. Yeah, like lower than 400, maybe between 200 and 400. That's about in the UV range. Does anyone know what size features are in transistors right now in Pentium chips? What node are they at? Pretty small. So they're at 10 nanometers, between 10 and 14 nanometer features now, and they're trying to get to 7 nanometers. So laptops have gotten a lot better, phones have gotten more powerful, and that's due to better CPUs and better memory. And of course, gaming has gotten more powerful and more realistic. GPUs are just another form of integrated circuit. And those chips in memory, CPUs, GPUs, those all have features on the order of between 7 and 14 nanometers, which is more than 10 times less than UV light. And there's a bunch of cool tricks that they play in order to make those very small features. But the problem that the computer chip industry is getting to, or the microprocessor industry is getting to, is that it's getting very difficult to make things that are smaller than 7 nanometers or 5 nanometers. But what do we know about that has dimensions kind of on the nanometer scale that we can work with? Molecules, polymers, nanotubes, things like that. So they're trying to come up with new ways to increase this transistor count. And this is an old Moore's law plot now, but this is showing that computing power doubles every 18 months. But you're getting to the point where it's hard to pack more and more transistors in a smaller and smaller space. So people are starting to try and use nanotube transistors. They're trying to use block copolymers or single polymer molecules in order to make these really, really small features. And so if you graduate or go to graduate school or go work for Intel or one of the other big semiconductor places, this is a constant thing that they worry about. All right. So we're going to talk about conductivity. That was just an intro where polymers are already contributing to the digital age, but we're going to talk about what's next in terms of what polymers and organic molecules are going to do. So when we think of conductivity of polymers, as we just discussed, a lot of conductivity of polymers is way down here. So the unit of conductivity is Siemens per meter, and that's Siemens as in the company Siemens, named for a German scientist who started the company. And so you see that even insulators like glass, like PTFE, like polyethylene have some finite electrical conductivity. So this is electrical conductivity. But it's really, really low, right? Silver, copper, graphite are up here, 10 to the 6th conductivity or so. And semiconductors are sort of in this range. And so they're called semiconductors because they have intermediate conductivity between what we think of as insulators, 10 to the minus 10, 10 to the minus 12 Siemens per meter, and good conductors like metal and graphite and things like that that have 10 to the 6th or 10 to the 8th Siemens per meter conductivity. What people have really tried to think about lately, since there was a Nobel Prize in conducting polymers, and I'll show you that in a second, is can you make electronic materials out of organic molecules? So before, let's say 1980 or before people really started to work on semiconducting polymers, everyone thought of polymers as insulators. But if you can mimic the properties of metals in an organic material, there's a chance that you could have metallic-like conductivity in polymers. So how do metals conduct electrons? What is the key feature of metals that makes this happen? They have free electrons, or they have metallic bonding, or they have lots of electrons that are not tightly associated with the nuclei. So when you look at the structure of silver, copper, iron, those other metallic conductors, they've got metallic bonding in their lattice, but they have lots of free electrons that can move throughout the system. And so the question is, can you make those free electrons in a polymeric material? That's what we're going to talk about today. And so right now, there are organic photovoltaics or solar cells made out of polymers. We'll talk a little bit about that. There's organic light emitting diodes. You've all heard of OLED screens and OLED TVs and everything else. Those are organic molecules that emit light. And people are really starting to work on flexible OLEDs for displays. And the key is that things that emit light sometimes have enough free electrons in order to conduct electricity, or at least be semiconductors. And we'll talk about the correspondence between visible light emission and conductivity in these materials. So the way to make electrons move in organic materials is this phenomenon called delocalization. You've already talked about delocalization in resonance structures in organic chemistry, right? So what's a molecule that you know has delocalized electrons? Benzene. That's a good one. And we draw a benzene with alternating single and double bonds, but that means that the electrons are delocalized around all those 6 carbons. So if you take something like benzene and convert it over to a polymer, and this is polyacetylene, so the monomer is this. And then how are we going to polymerize acetylene? So this is acetylene monomer. What type of polymerization? Whoops, what type of polymerization does it undergo? It's going to do a chain growth polymerization, right? And you're going to go to so remember, we take an electron, move it this way. We take an electron, move it that way, and we still have the double bond, but we've made a covalent bond to each monomer unit. And now if you look at this structure closely, you have a single bond, double bond, single bond, double bond, single bond, double bond. And I've drawn it out here, double bond, single bond, double bond, single bond, just like benzene. And so this polymer now has delocalization along the backbone. And we've taken this acetylene. It's nothing special that we did in terms of chain growth polymerization. It just has a triple bond to start with. And so that means we get a residual double bond because we've just taken 1 electron on each side. And now we have pi electrons on every single carbon. So if you look closely, there's a sigma bond here and a pi bond. And every carbon that has a pi bond gets pi orbital, right? Or p orbital. Then you have a sigma bond here, then a double bond, or a sigma bond and a pi bond. So you have pi orbitals here. And it's the presence of these pi orbitals on every carbon that allows this delocalization. So all of a sudden, we've started to delocalize electrons. And so we can't associate those electrons very closely with any atom like we can for polyethylene. Everything's stuck in sigma bonds, right? And so now we've started to create a delocalized structure that's a lot like metals in this polyacetylene. Does everyone get that? Does everyone get this picture? Okay, there's a good chance I'm going to ask you about delocalization and, you know, what are the ingredients that you need for turning a non-conducting polymer into a conducting polymer. So the first couple of slides here are pretty important. So it turns out when you start to delocalize electrons, you get this thing called a band gap. Now, it turns out everything has a band gap because there's always pi star or anti-bonding orbitals. But in something like ethylene, which is just a garden variety small molecule organic, there's a huge gap between your pi and pi star orbitals. And so you can't access that gap very conveniently. But as you start to increase Where's the other one? There we go. As you start to increase delocalization, or conjugation, that's called, or increased conjugation. Yeah. The band gap, or the distance between the valence band or where the electrons sit when they're in their orbitals in their ground state, and the conduction band gets smaller and smaller and smaller. And the conduction band is where the action happens in terms of conductivity. Metals don't have any band gap. That's why they're very good conductors. But the smaller and smaller we make that energy gap, the easier it is to take electrons from here and put them in the conduction band and start to get polymers that are conductors. And so because this gap exists, this exists in semiconducting polymers. So semiconductors, they have lower conductivity than conductors, and they have a finite band gap that's measurable. So those are two distinct characteristics of semiconductors. But now you notice that for ethylene, butadiene, those aren't very good conductors. They have a huge gap. Octatetrene, not that great either. But now polyacetylene has a small enough band gap that can be accessed and is classified as a semiconductor. Okay, and this is the same thing shown here. So that's a little bit esoteric, but it's this key of conjugation decreases band gap to a useful value. So I told you that in order to get conducting polymers, you can take an electron from here. Let me write that as an electron. An electron from here and excite it up into the conduction band that it can move. Does anyone know what happens when an electron goes from the conduction band in excited state and relaxes back to the valence band, the ground state? Yes. It can emit a photon. So you excite an electron from valence band to conduction band. So you can get conductive properties, you can do other things. How do you excite an electron? Does anyone know how you excite an electron from one level to the other? You can use light, you can use voltage, you can use lots of different ways to excite that electron. And when electron relaxes from conduction band to valence band, it can emit light. So this is exactly how OLEDs work. So an OLED is sitting there, it's a material, all the electrons are in its valence band. And then what do you have to do to an OLED to turn it on? Connect it to some electricity, right? And put a voltage across it or excite those electrons. So OLEDs have electronically excited electrons. You put a voltage across it. Those are the wires. The electrons go up into the conduction band and then they relax right down and emit light. So all you're doing is turning electricity into light in this OLED through this process. And that's the basic story of OLEDs. And what's cool is that you can get different colors of light emission depending on the band gap. So this gap tells you how much voltage you need or how much energy you need to excite that electron, but it also tells you the energy of the photon that's emitted when that electron relaxes. So if it's higher energy and it falls across a larger band gap, so higher energy photons have longer wavelength or shorter wavelength? Shorter, that's right. So if you want something to emit in what's a short wavelength visible color? Blue, purple, green is right in the middle. So you can engineer the band gap to give you blue emission, purple, not really purple, but blue or green emission. And then what's a long wavelength color? Red, so you can decrease that band gap so you can have less energy that those electrons relax across. And then you get longer wavelength emission to get red out of your OLED. And what colors do you need to make a display? Red, green, and blue, right? So if you can get those three, and then you might have a white light emitting OLED as well for natural lighting or something else, which is a mixture of all of them. But if you can get red, green, and blue, you can make an RGB display that plugs right into current electronics. So that's exactly what they do when they design these light emitting organic molecules. Now, OLEDs are usually small organic molecules, but the same lessons apply. There's such a thing called PLEDs, and you can buy a PLED TV that's a polymer organic light emitting diode. So, you know, that's just how it is. But you can engineer the polymer structure now to give different band gaps. And these are gaps in electron volts, and you can see for modeled and experiment, they can predict pretty closely what colors, or at least what energy photons will come out of this material. And so that's cool. Now you can pick some monomers, you can try and figure out what the band gap is, and then you can see how that emits light in an OLED, and you can put together an RGB display. And that's exactly what Philips and Samsung and all the big Sony and all the big TV makers have done over the last 20 years, is figure this out while they were making plasma TVs and LED TVs and cathode ray tubes and all the old TV technology that sort of passed us by. Now we're at OLEDs. Any questions? Yeah.
What's the difference between OLED and QLED?
So QLED is quantum dots. So instead of having a single organic molecule or a polymer, does anyone know what a quantum dot is? A quantum dot is, oh, go ahead.
I was gonna say they're like nanoparticles, and if you tune to different like wavelengths of emission from like different sizes.
Perfect. Yeah. So a quantum dot basically does quantum emission or emission of photons in a very defined range. That's why they're called quantum. And as Marcus said, you just change the number of atoms, or you change the constituent of the atoms from like selenium to sulfur or cadmium to tellurium, and you can get the same exact phenomenon. So organic molecules, conjugated polymers, quantum dots, and then there's a bunch of inorganic compounds that also do this. And so that's a really good question, because you can buy what Samsung sells, the QLED, right? Yeah. Okay, cool. And all of those things have a band gap. So their band gaps sort of happen by different physics. So if you go and study solid state physics, there's a lot of details here. But all of those materials that emit light have a well-defined band gap that controls the wavelength of light that's emitted. And so you open up the band gap, you get things that are more blue or short wavelength emission. You make the band gap narrower and narrower, you get green and then eventually red, or lower energy emission once you excite that. And all OLEDs are pretty much excited by voltage, right? Because we can control the voltage across a transistor or an OLED easily. Good. All right, clicker question. Which of these polymers is not conductive? Is D even an option on your clickers? I think it is. Yeah. I just want to see who's here. So let's look, let's analyze this. Okay, I've got a pi bond here. I've got a pi bond here. We got a pi bond here. Got a pi bond there. Sulfur has a lot of extra electrons on it, right? And so it looks like I have delocalized structures in B because of course this is connected to another pi bond right there. Same with polypyrrole. It's got pi bonds there. So I have delocalized electrons. Great. And then polyphenylene vinylene, same thing. I've got delocalized electrons. I have one here, and I've got pi bonds in my backbone. So they're all conductive. And so this is important because if I give you something like this, does this polymer have long-range delocalized electrons across its backbone? I've got pi bonds here, got pi bonds here, sp3, and then I've got pi bonds here. So this breaks conjugation. So there's delocalized electrons across this double bond, but this would be an insulating polymer. Because no long range delocalization. So if I ask you a question about this on the final, you want to look for, does every single carbon have pi bonds or p orbitals in it? That's what gives us delocalization. Great. So I told you that the Nobel Prize was awarded for semiconducting polymers in 2000. People thought that the folks who invented UV photolithography were going to get a Nobel Prize for a long time. They probably won't. And so Grant Wilson and Jean Fréchet, one was at Cornell, the other's at UT Austin. They probably won't win a Nobel Prize in chemistry for photolithography, but Professor Heeger, Professor McDermott, and Professor Shirakawa did in 2000 for polyacetylene. So they figured out how to make polyacetylene. Professor McDermott was a chemistry professor at Penn. This was discovered at Penn in his lab when Professor Heeger was a visiting scholar and Professor Shirakawa was a graduate student. And so they figured this out together. And you can still go see talks from Professor Heeger. He's a professor now at University of Santa Barbara. You can go see him at ACS meetings. You know, Professor McDermott just passed away a few years ago. But these are folks that are still around and invented some of the cool things about polymers that we're talking about today. All right. Oh, and this was the letter that they wrote in 1977 talking about their invention. So you can go look up this paper and read the Nobel Prize winning work, and they talk about delocalization and doping of polyacetylene, CHX. Very interesting. All right. So the one thing, let me see. Yeah. So if you read this paper, they do talk about doping. And the one thing that doping does is it helps you with a little bit more delocalization. So doping increases conductivity. That's a detail. If you ever hear about doped semiconductors have a little bit higher conductivity than undoped or intrinsic semiconductors, but we won't worry about that. What we will worry about is now, in addition to emission of light and conductivity, now you can train polymers to take on different colors depending on the state of doping and depending on the chemical structure of that polymer. So when something changes color, what are we seeing? What's happening to that polymer? So, you know, I look at this this door frame, right? And it's green. What is the paint doing on that door frame that allows me to see it as green? It's not emitting, it's not a light source, because if I turn off the lights, it's not emitting anything, but it's what? It's reflecting what? It's reflecting green to my eyes. That's why it looks green, right? And it's doing what to all other wavelengths? Absorbing them. And so now, based on that gap, we can change the polymer to reflect some light or transmit some light and then absorb a lot of other colors. And it turns out that you can reversibly turn these off and on. So has anyone heard of transitions lenses? Those eyeglass lenses, you go outside, they turn dark. So that's a photochromic inorganic molecule. It's actually PPG makes those now. Transitions was a big deal at PPG. They were actually trying to make paint do that. And it turns out they discovered an application in eyeglasses. But anyway, that's just a photochromic inorganic dye that's sitting there in the eyeglass lens. But if you've ever flown on a 787, a Dreamliner, not only is it made out of mostly high performance carbon fiber, but instead of a window shade that you raise and lower, it's got a little button where you can make the window more transparent or make the window less transparent. And what's happening with that little button is that it's causing an electrochromic response. So this is electrochromic, which means it's using something with electricity to change color. Photochromic is light to color, just like a transition lens. Now this is electrochromic. So you can change the color of these polymers or the transparency of these polymers by adjusting the voltage. And so what's interesting is, again, as you change the chemical structure, you can get different colors of electrochromic polymers. So people are thinking about these for displays. People are thinking about these for transparent solar cells, architectural features. If you have a big skyscraper, right, that's a lot of window shades, it's a lot of dusting, it's a lot of motors. Maybe you should just build this right into the glass so you can control all this electronically with no moving parts. All right. So we already talked about OLEDs. I'm going to skip the OLED part, and I think I'm going to go to solar cell part, if I can find it. Yeah. So you can read about nanotubes if you want. We'll count nanotubes as polymers. There's been a Nobel Prize on that. But one of the big applications of semiconducting polymers that are coming up are organic solar cells, or solar cells that are made basically out of carbon, hydrogen, nitrogen, and sulfur. Why would we want to make solar cells out of those elements versus what do we make solar cells out of now? What's the primary material? Silicon, right? What else do we make out of silicon? Computer chips. And so as we make more and more solar panels, and there's more and more computer chips needed in the world, now they're competing for the precious resource of refined silicon, which comes from really nice beach sand. And if you're interested in some of the processes that they use to make refined silicon, it turns out that beaches are being robbed of sand in Indonesia, in Southeast Asia, because that's where all the silicon foundries are, and that's where they have the really pure sand. So beach theft, it turns out, is a real issue in some parts of the world. Yeah. Google it. It's crazy. So anyway, silicon is getting harder and harder to make, and there's more competition for silicon, especially since we need to make a lot more solar panels. But there's no shortage of carbon and hydrogen and sulfur and nitrogen in the world. And so we're really interested in making solar cells out of these perhaps more renewable materials, granted if we can recycle them, than some of the things in solar cells nowadays. So what does the solar cell do? What's the basic function? Converts photons into electricity, right? And so if we go back to our band gap diagram, a photon comes in, strikes an electron in the valence band, excites it up to the conduction band, a higher energy, and then we can harness that energy by hooking a wire up to the solar cell. So it's exactly the opposite of an OLED. An OLED, you put electricity across it, out comes a photon of light. In a solar cell, a photon of light comes in, you have wires hooked up to the solar cell, and you can harness that electricity. And the way that they do that, and just to show you an example of a polymer solar cell, has anyone ever seen these funny purple solar cells that are on top of a bus station, or if you've seen them on a like a high-tech backpack or a tent? So anything that's purple like this is usually an organic photovoltaic. And in Berkeley, they have them on the bus roofs, and they made the roof wavy to show off that this is not your typical garden variety solar cell. They could have made the bus roof flat and just put a silicon solar cell on it, but they wanted to use these organic photovoltaics. So anyway, what happens is that a photon comes in and excites this polymer. Electrons from this polymer. And it turns out the electron goes into this fullerene that's a good electron conductor. So this is a good electron conductor. So you can get that electron out of the solar cell. But if you take a mixture of this fullerene and this semiconducting polymer, that's what gives it the purple color, and that's how you can make a solar cell. And that in general looks like this. And so you excite, as I just drew this diagram, you excite the polymer, you excite an electron in the polymer, it's transferred to the fullerene and then conducted out of the cell. So that's very simple, and people have worked hard over the last 20 or 30 years to make these organic photovoltaics, where now sunlight comes in, excites the polymer, and then we have two electrodes. So we have our anode, and then we have our cathode, and of course we have positive and negative voltage from that we can harness. Does anyone know what ITO is? Indium tin oxide. So indium is a precious element. It's hard to get. Tin is poisonous. And of course, oxygen is fine. But they use indium tin oxide because it's transparent, but it's also conductive. So this is a transparent conducting oxide, which is another huge field. In addition to trying to teach polymers how to conduct electricity, maybe so everyone can see that, people are really trying to come up with other transparent conducting oxides to replace indium tin oxide, which is hard to make and is not the best material ever. And so making transparent conductive materials is really interesting to help enable new solar cell technology, because you need to get the light in there somehow, right? And we usually use metals in this case, calcium or lithium, in order to conduct electrons and be electrodes. But for a solar cell, you need some sort of transparent material for that. Any questions or comments on this? Okay. So the takeaway is polymers are really important for electronics, and you can check things out in that area. And again, as I said on the final, there'll be a few questions for you about these topics. One other thing that I want to cover, and I'm going to put up just a couple more PowerPoint slides in this, is that we're going to move on and we're going to talk a little bit about, oh yeah, I'll ask this clicker question next time. But we're going to talk a little bit about 3D printing and how some of the things that we've used in this class, or some of the things we've learned in this class, is readily applied to 3D printing. So who here has done any 3D printing? What type of polymer did you use? PLA, that's the big one, right? What type of polymer is PLA? Does anyone know? It's glassy. And so what did the 3D printer do in order to print PLA in the first place? It melts it, and then it cools really quickly. And so what temperatures do we care about that are intrinsic to PLA that are important for 3D printing? TM and TG. And so when you walk up to the 3D printer, you're going to print PLA. What do you have to input in the printer in order to be successful? Printing temperature, you have to tell it how fast to print, all of those things. And so if we look at this diagram, where we have modulus versus temperature, printed parts, we usually want a high modulus, right? So this is a glassy, glassy modulus. TG, we get some rubbery, and then TM. And so we have to be at a high enough temperature, but we also need enough cooling so the part keeps its shape. So we can relate what we've done in 3D printing right to what we know about the thermal properties of PLA, and you can't go too high in temperature or you get degradation. Has anyone ever done any other type of 3D printing other than MakerBot style? What type did you do?
Well, other than plastic, I've done PBAX printing before.
Yep, PBAX. So PBAX is a thermoplastic elastomer, so it's a little bit more elastic. Or if you printed NinjaFlex, same thing. Has anyone done any other type of printing? Yeah, go ahead. ABS, that's right, that's thermal printing. Does anyone know another type of print besides MakerBot style or FDM?
I mean, I use a 3D pen sometimes.
Yeah, same thing.
Same concept, like it's stereolithography.
There's stereolithography. So has anyone done SLA printing? So it turns out that what we just talked about in photolithography is applicable to stereolithography as well. And so stereolithography, what it does, well, that's not the right diagram. So SLA uses light to solidify polymers. Does anyone know how that happens? How do you take a liquid polymer and shine light on it and get a solid polymer? It's like UV, it's exactly UV cross-linking and also UV polymerization. Where did we study UV photopolymerization? What type of reaction? Chain growth, free radical, photopolymerization. So remember we talked about AIBN and benzoyl peroxide, or we talked about benzophenone, which is a UV photoinitiator to initiate those radicals. and then they'll do free radical polymerization of acrylates or other things like that. That's the exact chemistry that's used in almost all stereolithography 3D printing resins, where you have a liquid resin and then you shine light on it and turn it into a solid, and you can build up a 3D model of that. Okay, so check out SLA, watch some YouTube videos on it, and we'll talk about 3D printing next time. We'll fill in a few gaps for the final. Take a look at the practice final and office hours, and I'll see you on Wednesday.